Good morning, everyone. Today we're going to talk about a comparison test for improper integral. Think about there are two airplanes. One goes above and one goes below. The corresponding trajectory for them will be the graph of f and g, with f greater than or equal to g and greater than or equal to 0. For all x greater than or equal to a, that is, f and g are both continuous positive functions on the interval from a to infinity. Now let's discover this together. If the area under the top curve f is finite, then so is the area under the bottom curve g. Since the integral of the function f from a to infinity corresponds to the area under the curve, we have, if the integral of this function f from a to infinity is convergent, then the integral of this function g from a to infinity would be convergent also. If the area under the bottom curve g is infinite, which means the improper integral of g from a to infinity is divergent, then we're going to have the area under the top curve f will be also divergent, which means the improper integral of the function f from a to infinity will be divergent also. Be careful though, the reverse is not necessarily true. If the integral of g is convergent, then the integral f may or may not be convergent. And if the integral of the top function f is divergent, then the integral of the bottom function g may or may not be divergent. Let's use the comparison test to determine if the following integrals are convergent or divergent. Let's denote the comparison test by CT and denote convergent here by C and divergent here by D. First, this improper integral of the function, the quantity of 1 plus e to the negative x divided by x, where x goes from 1 to infinity. Let's use the comparison test to determine this improper integral is convergent or divergent by comparing this integral with another improper integral of a positive function. On 1 to infinity, this function that we integrate with looks like this. Compare this function with another positive function that's easier to find untitled t, easier to find the integral. On 1 to infinity, this function that we integrate with is a positive function because you see this part right here, e to the negative x, is always greater than 0. Because the base e is positive, about 2.7, so base e raised to the n exponent is positive, so 1 plus a positive number divided by x, where x goes from 1 to infinity, is positive. We want to compare this positive function with another simpler positive function. So let's take away this complicated part, e to the negative x, and we have 1 over x. The function that we are integrating with is greater than 1 over x because it has a bigger numerator and both of them are positive functions. Now let's compare this with the improper integral of 1 over x goes from 1 to infinity. Do you guys remember this improper integral is convergent or divergent?
Divergent, right?
Yes, you got it. Okay. Why? Do you guys remember?
Because the power of x is to 1 and it has to be greater than 1 to be convergent.
Yes, you got it. I'll give you a thumbs up. Okay. Okay, good job. Okay. Remember, early on, we investigate improper integral of this type 1 over x to the p power, x go from 1 to infinity. It is convergent if and only if the power p is greater than 1. So this integral here is going to diverge. It diverges to positive infinity.
Can I ask a question, please?
Yeah, of course.
How do you know? Like, is there any way to find a a function to compare it with? Like,
you had to, yeah, it's a tricky part here. So how do you find to compare this function with this function? This integral, right?
yeah.
So that we're looking for basically you had to take a look at the function and think about what will be a simple function related to this. That we integrate so if I take away this part, I get 1 over x. This function, and what happens to this part? This part over here if the is always positive. So that's why I want to compare with 1 over x. It's kind of like you trying to take part of the function and think about to relate to a function that is simpler. Okay, so I take 1 over x, so, which is part of the function. Test. And this part here is always positive. That's why I compare this with that. But it's kind of like a try and error. So if it doesn't work, then you can try other. Okay. Yeah.
Okay.
So if you take away this. Okay. Yeah, that was a tricky part. That's a very good question. Now back to this integral. What do you think? Is this integral here convergent or divergent? So this function is always above this function and both are positive functions. So if the integral of this lower function is divergent to infinity, then the integral of this top function will be divergent and diverge to infinity also by the comparison test. So we have just proved this. This improper integral here is divergent.
Can you repeat the part about like finding a appropriate function to compare to? Because I'm still a little bit confused about that. Do you kind of just like use your like common sense to kind of find something, or is there like a systematic way to do it?
You had to do some try and error, and also you had to look at the part of function, and you just need to take away some part of it and compare that with that. Yeah. So it takes some skill. It takes some practice. Okay. So over here I take 1 over x. Yeah, that's yeah. You had to try it. Yeah, there's no say it's not like a machine. You just put this in and there's no. You have to experiment with it. Yeah.
Okay, thank you. Awesome.
Example 2. Is this integral convergent or divergent? This integral x goes from 0 to infinity. So on 0 to infinity, we're going to compare this function with another positive function. Compare with what? Okay. Now let's just take away some part of the function. So then how about we take away this 1? Okay, take away this 1. So we have x over x to the 5th power. So make it simpler that way. Okay. So we're going to compare that with x over x to the 5th power over here. Okay. So which one's bigger on 0 to infinity? The bigger the denominator, the smaller the quotient, right? So this is smaller. Okay. So that's bigger. And both of them are greater than 0 because we're talking about from 0 to infinity. Now this one over here, it is equal to 1 over x to the 4 power, which is a simple function. We know how to integrate, okay? On 1 to infinity, we look at this integral of 1 over x to the 4 power, x go from 1 to infinity. It is convergent because the exponent on this x here is 4, it is greater than 1. By the comparison test, this integral x over x to the 5th power plus 1, x go from 1 to infinity, will be convergent also because it is a positive function below 1 over x to the 4. Now we're finding this integral from 0 to infinity, so we break it into two parts. The first part will go from 0 to 1, the second one go from 1 to infinity. The first part over here, it is an ordinary definite integral, and it corresponds to the area under the curve from 0 to 1. The yellow highlighted part. It is a finite number. The second part here is an integral that converts to a finite number also. So the sum of two finite numbers is again a finite number. So this integral here converge to a finite number.